Yes, dear friends, we are now entering into an entirely new chapter that is related to hybrid orbitals. That is, we are talking about hybridization. And in going details of the hybridization theories, we must learn about the transformation properties of atomic orbitals as a primary concern. I'm your instructor, Saurabh. Let's begin with the job. When we talk about the transformation properties of atomic orbitals, the wave equation that is very prominent is the Schrodinger wave equation, and that takes the shape as you can see, as that is the lambda square psi plus 8 pi square m upon h square into e minus v psi is equal to 0, where psi is the wave function, and this lambda square, this is the Laplacian operator that has the value in the space del square upon del x square plus del square upon del y square plus del square upon del z square in the entire space. Of course, this is known as Laplacian operator. Everybody is knowing about it. And the E stands for the total energy, while V stands for the potential energy. So E minus V is actually the kinetic energy of the system. So the Schrodinger wave equation in its simplest form is represented by either the equation demonstrated or H psi is equal to E psi. However, when we talk about the circular system, because when we are interested in talking about the orbitals, we are talking about the shapes of orbitals, then what we need to take care of is that the Cartesian coordinate equation must be transformed into a polar coordinate system. And in doing so, we are actually avoiding all the mathematics. Only we are believing that the rest of the basic things that we know, that if P is transformed to P dash, a point P transforms to P dash along an angle theta and phi that has been demonstrated in the figure, and the radial distance r, then the coordinates x is equal to r sine theta cos phi, y stands for r sine theta sine phi, whereas z stands for the cos theta only. Here the radial distance theta is the angle between OP and z axis, and phi is the angle between x axis and the projection of line in xy at the point along OP dash. So that is how that transforms. When you talk about the Schrodinger wave equation, it has two major components. The first component is the radial part. The radial part depends upon only the principal quantum number n and r, and which depends on the distance of the electron from the nucleus, and therefore is unaffected by symmetry operation because it does not keeps on changing its transformation properties. However, when you talk about the second part that depends upon both the values, that is theta and phi, that is the angular part of the wave function, and these are actually affected by the symmetry operations. The normalized wave functions that has been observed and computed from Schrodinger wave equation takes the shape that if you talk about n is equal to 1 and l is equal to 0, m equal to 0, of course you are talking about s as the principal quantum number. The normalization factor is 1 by root pi by 2. When this 2, the normalization function is under root 3 pi by 2, and the angular part is equivalent to cos theta. When this orbital is when n equal to 2, it still have the py orbital or pz orbital. They have all values same under 3 pi by 2. Only thing is, along the y-axis, the value changes to sine theta, sine phi, and along the y-axis, that is sine theta, cos phi, that we have seen earlier also. Interestingly, the situation when it is developed that dz square, which is equivalent to 3 cos square theta minus 1, that we'll see later also, is now in terms of its normalizing factor is under root 5 by pi and divided by 4. Similarly, the other orbitals like dx square minus y square is equal to the same value with the value of angular part sine square theta cos 2 phi, and the rest of the elements dxz, dyz, and dxz have certain values that have been displayed like sine theta cos phi, sine theta cos theta sine phi, sine square theta sine 2 phi. They are not really very important, but sometimes they make a very prominent influence on the calculations. When you talk about a general thing, when you talk about the dz square orbital, the dz square orbital is reportedly having the 3 cos square theta minus 1, and the normalization constant is under root 5 15 pi by 4. If you want to manipulate this equation a bit, then you have 3 cos square theta minus 1 into bracket cos square theta plus sine square theta, that is nothing but equal to 1, and therefore it becomes 2 cos square theta minus sine square theta. And if I put again cos square phi plus sine square phi instead of 1 in multiplication with sine square theta, and if you solve for this, what you get is 2 cos square theta minus sine square theta cos square phi minus sine square theta sine square phi, that is actually equal to 2z square minus x square minus y square. So you can see that 3 cos square theta minus 1, that is equivalent to dz square, is equivalent to 2z square minus x square minus y square. So instead of writing dz 2z square minus x square minus y square, we generally write dz square. That's it. Angular wave function is equivalent to this, and therefore in most of the groups z square and x square plus y square transform the same way as does the 2z square minus x square minus y square transforms. So these are quite familiar shapes of orbitals. You can see this s orbital, px orbital, py, pz, and for the degenerate dxy, yz, and xz orbitals, you have dxy on the frame, and the rest of the d orbitals like dyz, dxz, and dx square minus y square and dz square, with the difference that for xy, yz, and xz, the lobes are between the planes, while dz square and dx square minus y square lobes are seen along the plane. That is the only difference, and therefore it makes a great difference when you talk about bonding. It will be very interesting to see how these orbitals transform under the operation in the particular symmetry. For working out the transformation properties of these, we must know that each orbital forms a basis for the representations of dimension 1, and hence it is an irreducible representation. So if it is an irreducible representation, how do you see? I mean, we can correlate in the character table itself. Rather, it remains positive when affected by symmetry operation, or otherwise it changes to sign. Let's consider these atomic orbitals for C2V case, C2V point group. When we consider a C2V point group, we have 4 operations E, C2, sigma B, and sigma B dash, that is sigma xz and sigma yz. If we talk about S orbital, which is spherically symmetric, all the operations are unmoved, unshifted, so therefore it obviously belongs to A1 representation. When you talk about PX orbital, what happens is along the x-axis, if you choose the identity, it's not going to change, but in case of C2, it is going to reverse. In case of xz, it is going to reverse, but in case of yz, there would be no effect for this, and it belongs to B1 symmetry. If you talk about py orbitals, for identities, no change. For C2, along the z-axis, there is a change. For sigma xz, there is sigma xz, there is no change, and sigma yz, of course, there is no sigma xz, it gets reversed, and sigma yz is equal to 1. When you talk about pz, pz is 1. Z-axis is the rotational axis, so identity is 1, C2 is 1. Sigma xz and sigma yz, they also remain unshifted, and therefore there is no change. It belongs to A1 type of species. Keep on performing the same thing like dz square, we will find that it belongs to A1 species, dx square minus y square. So dz square and dx square minus y square transform in the same manner as does the A1 operation, A1 irreducible representation rather, and the rest of the 3 dxy, dyz, and dxz transforms as demonstrated, and therefore they belong to A2, B1, and B2 kind of symmetries respectively, that you can see and work out for yourself. So the essence is you can take the orbitals as a basis and make them ensure that for any particular point group, they have particular notation extreme right of the character table in the 3rd and 4th column. So if you look at the character table for point group C2E, you will find that Z transform is A1. And x square, y square, z square, or x square minus y square, x square plus y square, and z square, they of course transform the same as A1. I'm sorry, it is x square plus y square, and A2 transforms as x and xy. B1 transforms as x that we have seen, B2 transforms as y, and xz, yz, xy planes transform according to B1, B2, and A2. That is quite easy to understand and to work out. So that's all for now. Let's talk about the more on hybridization in the next video. Thanks for watching.